This is lesson 13.6, Theoretical and Experimental Probability. The different ways an event can happen are called outcomes, and a simple event is one outcome or a collection of outcomes. You can measure the chance of an event happening with probability, which is a ratio comparing the number of favorable outcomes to the number of possible outcomes, assuming the outcomes are random, meaning that each outcome is equally likely to occur. So this is the notation we use for probability. This is read as the probability of an event, whatever that event happens to be. And that's equal to the number of favorable outcomes over the number of possible outcomes. Now, because the favorable outcomes will be less than or equal to the possible outcomes, probability of an event is always between 0 and 1 inclusive, which means it can be exactly 0 or exactly 1. The closer a probability is to 1, the more likely it is to occur. So let's take a look at the first example. Suppose a number cube is rolled. What is the probability of rolling a 4 or a 5? Well, the numbers that could be rolled on this number cube are 1, 2, 3, 4, 5, and 6. And this set of numbers is called the sample space. So we want to know the probability of rolling a 4 or a 5. Well, the number of favorable outcomes here are the 4 and the 5. So that's one outcome, two outcomes. So two favorable outcomes. Out of how many total? Well, 1 through 6 is 6 total outcomes. So the probability is 2 over 6, or if we reduce that, that's 1/3. Or sometimes we like to express probabilities as a fraction. This is a fraction, as a percent. So we know this is one of our common fraction to percent conversions that we should know. 1/3 is 33 and a third percent. So either of those answers would be fine. Sometimes it'll actually ask you for both versions, the fraction and the percent. So make sure especially that you're refreshing your memory on some of those common fraction to percent equivalents. All right, example 2 says, suppose two number cubes are rolled. Find the probability of rolling two identical numbers. Okay, well here we have two number cubes being rolled. So in order for the numbers to be identical, we need the number on one number cube to match the number on the other one. So in this case, the sample space is not as simple as just listing out 6 numbers. It's actually listing out pairs of 6 numbers paired with 6 other numbers. So we're actually going to make a small table to show the sample space here. Well, it's actually not that small of a table, but a table nonetheless. So let's say first you roll a 1. Well, your options for the second die, or the second number cube, would be another 1, or a 2, or a 3, or a 4, or a 5, or a 6. Oops. Okay. Now, let's say the first number rolled is a 2. Well, the other options would be a 1. Oops. Got that a little bit backwards there. A 2, a 3, a 4, 5, or 6. And then the same thing for 3, and of course the same thing for 4, and for 5, and for 6. So let's go ahead and fill these in. And this may seem like it's kind of pointless at this point. We'll see in a minute why it's important to actually have all of these listed out. Okay, all the pairs for 5. All right, and the last one with sixes. Okay. All right, now the part of the reason that we have to list this is because we have to make sure that we're counting things that look kind of the same as two separate outcomes. So for example, let's take something really simple, like a 4 and a 1 compared to a 1 and a 4. Now, technically, you wouldn't, normally when you roll two number cubes, you can't tell the difference between one and the other. However, these are two different ways to get the exact same outcome, or a very similar outcome anyway. So they do actually need to be listed. For this purpose, imagine that one of the number cubes is red and the other one is blue, for example. Rolling a 1 on the red die and a 4 on the blue die might give you the same two numbers, but it's not, in terms of probability, equivalent to rolling a 4 on the red one and a 1 on the blue one. So we do actually have to list out the outcomes so that we make sure that things like that that look similar are actually not counted as one single outcome. Well, now we want to find the probability of rolling two identical numbers. So let's look through our table and find the ones that have identical numbers. Well, you could roll two ones, two twos, two threes, two fours, two fives, or two sixes. So the number of favorable outcomes, there are 1, 2, 3, 4, 5, 6. And the total number of outcomes, there's 6 here, 6 more is 12. This is 18, 24, 30, 36 total. All right, and of course we'll reduce this fraction down to 1/6. And then if we change this to a decimal and then to a percent, 1 divided by 6, and then move the decimal over 2 places, this comes out to 16.66666 repeating, which of course we know that 6 repeating is just 2/3. So there are our answers for example 2. Okay, the probabilities in the examples above are theoretical probabilities. Theoretical probability is the chance that an event should happen. So the probability of rolling two identical numbers, you haven't rolled anything yet, it's theoretical. Same thing with the probability of rolling a 4 or a 5. The number cube has not been rolled yet, it's theoretical probability. The experimental probability is what actually happens when an experiment is repeated a number of times. So in this case, the probability of the event, the experimental probability, is the number of favorable outcomes that have happened over the number of outcomes that have happened. So in experimental probability, you're talking about something that has already happened. So for example 3, it says a coin was tossed 40 times and heads came up 18 times. So we first want to find the experimental probability of getting tails for this experiment. So we want to know the number of favorable outcomes that have happened. So if we're looking for the experimental probability of getting tails, we want to know how many times tails has happened. Well, if a coin was tossed 40 times and heads came up 18 times, then that would give us the remaining 40 minus 18, or 22 times that tails came up, because there's only two possible options for a coin. It's either heads or tails. So since heads came up 18 times, tails must have come up the remaining 22 times. So 22 out of the number of outcomes that have happened. Well, if the coin was tossed 40 times, that is the number of outcomes. Okay, and if we reduce this, this reduces down to 11 over 20. And again, we want to write this as a fraction and as a decimal. So 11 over 20 is equal to 55%. Okay. And part B says compare the experimental probability in part A with the theoretical probability of getting tails. Okay, so the experimental probability we just found of getting tails, so that's what we were talking about here. This was 11 over 20, or 55%. The theoretical probability, remember, has nothing to do with the experiment. It's just based on theory. So if I handed you a coin and I said, what is the probability of getting tails? You, of course, would tell me that there is one possible way to get tails out of two possible outcomes, heads and tails. So those are your two outcomes. You're looking for the probability of just one of them, which is tails. Well, 1/2, of course, we know is 50%. So we can see here that in theory, you should get tails 50% of the time, but in the experiment, they got tails 55% of the time. So we could say that getting tails occurred more often than expected in the experiment. So because the experimental probability was 55%, which is higher than the theoretical, which is 50%, getting tails occurred more often than expected in the experiment, 55% of the time instead of 50%. Okay. Another way to describe the chance of an event occurring is with odds. The odds in favor of an event is the ratio that compares the number of ways the event can occur to the number of ways that the event cannot occur. The odds against an event are basically the exact opposite. The odds against an event occurring is the ratio that compares the number of ways the event cannot occur to the number of ways that the event can occur. So unlike the probability ratio, where part of the ratio is the total number of outcomes, for odds, we're dealing with the ratio of favorable outcomes to the ratio of, we could call them unfavorable outcomes. So let's look at example 4. This looks kind of similar to the question we answered in example 1. So in this case, though, we're not looking for the probability of rolling a 4 or a 5. We want the odds in favor of rolling a 4 or a 5. Well, we already know that the sample space includes 1, 2, 3, 4, 5, and 6. Well, to find the odds in favor of rolling a 4 or 5, we want to know the number of ways that the event can occur first. Well, in order to roll a 4 or 5, go figure, you'd need to roll a 4 or a 5. So there are two different ways that this event can occur. And we want that in a ratio with the number of ways that the event cannot occur. Well, either you roll a 4 or a 5 or you don't roll a 4 or a 5. So look at the remaining numbers. 1, 2, 3, 4 of them are neither 4 nor 5. So that would be 4 outcomes that are not favorable. And of course, just as if this were a fraction, a ratio of 2 to 4 can be reduced down to a ratio of 1 to 2. Okay. All right, for the try it yourself problems, there's kind of a mix of stuff here between probability and odds, experimental, theoretical probability. So go ahead and pause the video, take a little bit of time to answer those couple questions, and when you're ready to check your answers, press play. Okay, for the first one, the probability of selecting a yellow marble. This is 3/10 or 30%. For part B, the probability of selecting a blue or a yellow is 4 out of 10. Or when you reduce 4 over 10, it's 2 over 5, or 40%. We don't really like to leave fractions this way, so these are the two possible answers we'll look at. And then part C asks, what are the odds in favor of picking a red marble? And for this, there are 6 red marbles to choose from and 4 that are not red, which of course reduces to 3 to 2. Okay, the last example, example 2, says 10 marbles, or not example, the last try it yourself problem that you worked through says 10 marbles are selected from a bag of colored marbles. Results are shown in the table. We wanted the experimental probability of selecting a red marble. And you will have noticed that 4 times a red marble was selected out of 10 times total, which reduces to 2/5, which is 40%. Okay, You can also use past performance or a survey to predict future events. And what you'll see in section 13.7 is that this is not always valid, but for now we will assume that that the survey results or the performance of whatever the particular question is referring to is indeed a valid comparison. So let's look at example 5. It says Miss Newman surveyed her class to see which sports they preferred watching. 44% preferred football, 28% basketball, 20% soccer, and 8% tennis. Out of 560 students in the entire school, how many would you expect to say they preferred watching basketball? Okay, so if these percents from her survey are fairly accurate, then these percents should also apply to the population as a whole. So if we want to know how many people would say that they prefer watching basketball, we know 28% of Miss Newman's class liked basketball. So we know that's 28% out of 100%. Well, we want to know how many students are in this group. So across from the 28, we'll put an X. Out of how many people total? 560 students in the entire school. Okay, so there's a ratio that we can now solve, or a proportion that we can now solve to find X, which is the number of students in the school that would say that they prefer watching basketball. So we'll go ahead and cross multiply. We get 100x equals 28 times 560, which is 15,680. And then we'll divide both sides by 100. And we get that x is 156.8. And because we're talking about number of students, the most reasonable answer here would be about 157 students. Okay. The last try it yourself problem is similar to the previous example, so pause the video, work through that problem, and when you're ready to check your answer, press play. Okay, for this one you should have set up a proportion also. So how many of the 560 students in the school would you expect to say they preferred watching football or tennis? That would be 291.2, which would, since we're talking about, again, students, that would round to 291 students. Or technically about 291 students.